Alrighty, guys. So today we're going to be talking about two new gas laws. They're called Charles Law and Gay-Lussac's Law. Now, for your notes, instead of writing the full thing, because I know this is like two names, you can just write GL Law if you want, up to you. If you want, you can write C Law. I don't really care. Just an easier way to write it. I'll know what you guys mean. Okay? Okay, so last time we met, we talked about two characteristics of gases, right? We talked about pressure and volume. And so today we're going to be adding on one more characteristic of gases. And today we're going to be talking about temperature. So make sure you guys write this part down and make sure you guys write these two equations. Okay. So temperature, we symbolize it with the letter T. And temperature is how fast the gas molecules are moving. Yeah, I know in regular life we think about temperature as how hot it is, which is true. But the hotter something is, the faster the molecules move. So just make sure you guys jot that down. We measure temperature in something called Kelvin. We symbolize that with the letter K. So I know in real life or regular life, we usually measure temperature in Fahrenheit, right? So we measure it in terms of degrees Fahrenheit. But in chemistry, we have to measure it in terms of Kelvin. So we're going to use these two equations to turn Fahrenheit into Kelvin. Okay, so make sure you guys jot these equations down. I'll show you guys how to use it in just a second. Just make sure you have this highlighted part written down. All right, so to practice converting into Kelvin, let's I'm gonna bring up the weather for today in Long Beach, and it says right now it's 63 degrees Fahrenheit. Okay, so what we're gonna do is we're gonna take the weather right now and we're gonna turn it into Kelvin. In order to do that, we need to use these two equations. Somewhere on your paper for number one, I want you guys to write down that it is 63 degrees Fahrenheit. That's the weather right now, okay? All right, so what we're going to do now is we're going to use these two equations in order to turn this into Kelvin. Now, there's no one step that we need to take. What we need to do is we need to use both of these equations. So first, we're going to use this equation right here on the top in order to turn Fahrenheit into Celsius. Okay, so in order to turn Fahrenheit into Celsius, all we're going to do is we're just going to copy down this equation. Celsius is 0.56 multiplied by Fahrenheit, so 63, minus 32. Okay, so all we're doing is plugging in Fahrenheit right here. All right, so the math for that is pretty easy. All we're going to do is do the parentheses first. So we got 63. We're going to subtract 32. And so inside of the parentheses, we got 31. So we got 0.56 times 31. Okay, so on our calculator, super easy. We just need to do 0.56 times 31. Okay. And so we'll get an answer of 17.36 degrees Celsius. So 63 degrees Fahrenheit is the same thing as 17.36 degrees Celsius. Okay. So that's two ways you can talk about the temperature outside right now, 63 Fahrenheit or 17.36 Celsius. Okay. Any questions on how to turn Fahrenheit to Celsius? Hopefully it's not too bad. Again, you just need to plug in Fahrenheit right here, minus 32 times 0.56, and you get 17.36. All right, but we're not done because, again, for this unit, we always have to measure temperature in terms of Kelvin. So what we have to do is we need to turn Celsius into Kelvin. That part's really easy. All we got to do is take the Celsius, and we add 273.15. Okay, so if we add 273.15, that's going to give us the value in Kelvin. So 290.51 Kelvin.
Quick question is, can I ask about is that like, it's like let's say if I go to like Big Bear, it's higher up for 2 days.
If you have the same balloon, it would.
Same temperature here.
Yeah, it would depend on the temperature, and because the thing is here, it's constant pressure, right? But if you take it to Big Bear, it's a different pressure. So you would have to account for the pressure when you do that calculation.
Like chip bag will pop.
Yes, yeah. And that's because the pressure differential outweighs the temperature differential. Yeah. All right, so take a minute to copy down that equation. We'll be using that. I'll be right back. Okay, so again, guys, Charles' law basically tells us if you heat up a gas, it gets bigger, cool it down, it gets smaller. So I'll show you guys a quick demo just to show you guys what it looks like in real life. So here I got some soda cans, and then I've been heating them up. So since I heated up the soda cans, there's gas in the can, right? They're already open. So if I heat up the gas temperature is going to be high, right? So what I'm going to do next is I'm going to put the soda can face down into ice water. And so if I put the can into the water, what's going to happen to the temperature? Is the temperature going up or is it going down? It's going to go down.
It's gonna like.
Yes, exactly. So since I'm going to decrease the temperature, obviously we can, based on Charles' law, we can assume that the volume, the size of the gas is going to go down too, right? So let's see if that works here. I had a little mess up in my first class today, but if I put it in cold water, it's not going to work. Okay. Let's try with the other one. I have two just in case. Sometimes it doesn't work out. Yeah, it's supposed to crush. Sometimes I run into issues. There we go. So yeah, so as you cool down the gas, you guys can see how it crushed, right? Since it crushed, it's smaller now, right? So temperature goes down, volume goes down as well. I don't know what happened to that first, but that's an example of Charles. Okay. All right. Any questions on Charles' law? Yeah. No, as long as you have the equation and you understand the general principle, that's totally fine. Okay. All right, let's move on to the last gas law for today. We're only going to learn two. So the last gas law, it's going to look very similar to Charles' law. We're just replacing one of the variables. So the other gas law we're going to talk about today is Gay-Lussac's law, so GL law. Okay, and if you look at the formula, it's very similar to Charles' law. Okay, and so if I can just explain it, basically, if you heat up a gas, right? If you make a gas hotter, the pressure will go up, which makes sense because the gases are going to move faster. If it moves faster, it's going to hit stuff harder. Okay, so if you heat up a gas, the pressure will go up, and then the opposite is true as well. If you cool down a gas, the pressure will go down. Okay. So that is Gay-Lussac's law. Okay, so this is going to be our practice problem. We're just going to do number 3. We'll skip number 4 because it's pretty much what you're doing on your assignment. So first thing that you want to do whenever you have these problems is figure out which law you want to use. Okay, we learned 3 gas laws already. And on your assignment today, you're going to have all 3 on them. Okay, so if you were absent last time, make sure you finish last time's assignment because you're going to need to know how to use that first gas law before you do this assignment today, okay? But for the rest of us, let's figure out which gas law we want to use. Boyle's law, Charles' law, or Gay-Lussac's law, okay? So what we want to do is we want to look at all the numbers, okay? And figure out if it's pressure, volume, or temperature. So if you look at 12 liters, is 12 liters pressure, volume, or temperature? 12 liters, P, V, or T? If it's liters, is liters talking about how hard the molecules hit stuff, how hot it is, or how much space? Yeah, V. Okay, 12 liters is V. It's talking about volume. Okay, I'm gonna assume that you guys are just a little shy, but just make sure you're comfortable identifying these or you're gonna be using the wrong law and it'll mess up all your calculations, okay? So that's volume. Okay, it's collected at 38 degrees Celsius. Okay, so degrees Celsius is really easy. Is this pressure, volume, or temperature? Yeah, temperature, degrees Celsius is how we tell how hot or cold it is outside. Okay, it's asking us to find the volume. So what are we looking for, P, V, or T? V, yeah, we're looking for V. Okay, the gas will occupy at 39.9 degrees Celsius. Now, obviously, this one is temperature, right? Okay, so just by taking a look at all these, we got only V and T, right? Which gas law only talks about V and T? Look at your notes. Yeah, Charles' law. Yeah, Charles' law. Okay, so that's the first thing you want to do. Figure out which law you want to use. You just look at the numbers and look for if it's PV, VT, PT, whatever combination. Okay, so we're going to be using this equation right here. V1 over T1 equals V2 over T2. Okay. Does that part make sense? Just identifying the variables. All right. Next thing we want to do is we want to plug in our numbers into the right spot. Okay. All right, so you guys should have noticed that these first two numbers are the original conditions, right? You start at 12 liters and 38. Okay, and then this is going to be the new volume and the new temperature. So what we want to do is we want to identify if it's the starting or the ending. Okay, now, before we plug it into this equation, anyone know what we have to do first? It has to do with temperature.
Okay.
Yeah, we have to turn temperature into K. So we got to take T1, which is 38.8 degrees Celsius. And we want to take T2, which is negative 39.9 degrees Celsius. And we want to turn it into Kelvin. Okay, so we want to add 273.15 to both of them. Okay. And then after that, you can plug it into this equation and then solve from there. So I'm going to give you guys about 3 minutes. See if you guys could turn the temperatures into Kelvin and then plug it into this equation. If you want to try solving it, go ahead and do so. But in about 2 minutes, I'm going to show you guys how to do that. Okay, so at least turn this into Kelvin and put it in the right places for me. Okay, so what we want to do again is we want to turn the temperature into Kelvin. So the T1 is going to be 38.8 plus 273.15. Okay, so T1 will be 311.95 Kelvin. Okay. For T2, since it's negative 39.9, we can just subtract that from 273.15. If you did it a different way, that's fine. But as long as you ended up with 233.25 Kelvin, that's all good as well. Okay. All right. So now we're just going to plug it into this formula right here. So for V1, we got 12 liters. So we're going to plug in 12 liters. Okay. Next, we got T1, which is 311.95 Kelvin. Okay, for V2, that's what we're looking for. So we're going to put V2 right there. And then for T2, we're going to put 233.25 Kelvin. Okay, and what we want to do is we want to solve for V2. Okay. Okay, so let's do the math, and I'll show you guys how to do that. So what we want to do here is we want to make V2 by itself, right? So we need to move this 233.25 Kelvin to the other side. Okay, now the way that we're going to do that is first we need to figure out what we're doing here in the fraction. Remember how we learned that it's top divided by bottom? So if we wanted to rewrite this, another way we can rewrite this on the right side is V2 divided by 233.25. Okay, does that make sense? So what we want to do is we want to move this to other side, so we have to do the opposite. What's the opposite of division? It's multiplication, okay? So since it's multiplication, we're just going to multiply both sides by 233.25, okay? So on the left side, we're just going to multiply with this. So we're going to have 12 divided by 311.95 times 233.25. And that'll give you your final answer for V2. Okay. All right, so on your calculator, super easy. 12 divided by 311.95 times 233.25, and that's going to give you a value of 8.97 liters. Okay, that's your final answer.